Welcome to this calculus course. We will begin this course with a brief discussion on functions and limits. What is a mathematical function? We actually live in a sea of mathematical functions. All our interaction with our immediate surroundings can be linked in one way or the other with some mathematical function. For example, let's think about a student assistant working and earning $7.50 an hour. The amount of money the student makes actually is related to the number of hours the student works. And here is a relation. When the student doesn't work, the student doesn't really earn any money. The student works for 1 hour, the student earns $7.5, for 2 hours, $15, 3 hours, $22.50, and so on. Now, mathematically, we say that the amount of money the student earns is a function of the time in hours. Is that right? It's a function. What is the meaning that it is a function? That the amount of money varies. It depends. There's a direct relationship between the amount of money the student earns and the amount of hours that the student puts in. And we can write it like this mathematically: A of t. Now this is not A multiplied by t. This means A of t. A as a function of time is 7.5t. Now you understand this concept. A of 1 equal to 7.5. A of 2 equal to 15, A of 3 equal to 22.5, and so on. Now a function has an input and an output. In this case, the input is the time in hours and the output is the amount of dollars. When the input is 1 hour, the output is $7.50, and we say A of 1 equal to 7.5. Similarly, when the input is 5 hours, the output is $37.5, or A of 5 equal to 37.5. Now here we have a good description of a function. Now you are familiar with drawing the graph of a function, aren't you? Now what will be the graph of this function we just talked about, A of t equal to 7.5t? It will be a straight line, and the slope of that graph will be $7.5 per hour. It means every time the student puts in 1 more hour, the student takes home $7.5. So that 7.5 is actually a rate of change. The slope of the graph is a measure of the rate of change. When the input changes by 1 unit, how much does the output change? Okay, let's now talk about independent and dependent variable. In the function we just talked about, there are 2 variables. Time is a variable. The amount of dollars is a variable. Is that right? Now, one of them is the input. Which of them is the input? And which is then the output? Now, the input variable is called the independent variable. Why is it called the independent variable? Because the student or the people related to the student are free to decide the number of hours the student has to work. You see? And therefore, it is independent. And depending on the number of hours the student works, the amount of dollars depends on that. So in the function A of t equal to 7.5t, t is the independent variable because the student is free to choose the number of hours he or she wants to work. Is that right? Well, of course, the employer has to agree also on the number of hours. But that is independent. You can actually choose. And the output actually depends on the input. Therefore, the output is called the dependent variable. So if you look at the general expression that you're familiar with, y equal to mx. Y is the output, x is the input. X is the independent variable, y is the dependent variable. Always the dependent variable is the function value, right? Which is connected to the input of the function. The amount of money the student earns depends on the amount of hours he works, and therefore the amount is a function of the time t. Look at another example. The position x of a car moving at 2 meters per second is a function of time, and we can write it like this: x of t equal to 2t. The car is moving at a constant speed of 2 meters per second. That means every second the position of the car will change by 2 seconds. You have x of 1 equal to 2 meters, x of 2 equal to 4 meters, x of 3 equal to 6 meters. Each time t changes by 1 second, x will change by 2 meters, and therefore this 2 is the rate of change. Is that right? Each time the input changes by 1 unit, the output will change by 2 units. That's right. Time t is the independent variable, and x in meters is the dependent variable. All right. Having got some idea about a function, let's now talk about the domain and range of a function. All these ideas you know already, but let's refresh our memory on this. What is the meaning of domain of a function? Well, we said a function has an input and an output. Now, is it possible that all functions can have all possible numbers as input and all possible numbers as output? Well, not necessarily. So, the domain of a function is the set of all possible inputs for that function. Now, for the function we just talked about, a of t equal to 7.5t, what are the possible inputs there? Assuming that a student can work negative hours, we can say the input can be all possible values. Is that right? How about this function? X of t equal to 2t. Here the input is the time in hours and the output is position in meters. Now, I can actually use any value of t as an input. That will give me an output value. When x equal to 5, when t equal to 5, x equal to 10. When t equal to negative 5, x equal to negative 10 meters. So the position of a car can be positive x or negative x. That's right. So you can actually take any number from the set of numbers from negative infinity to positive infinity. It can be used as an input here. Therefore, we say the domain of this function is the set of all real numbers from negative infinity to positive infinity. In the same way, your function a of t equal to 7.5t, the domain is the set of all real numbers. How about this? F of x equal to x over x plus 4. There is a little problem here. What is that problem? When x equal to negative 4, the negative 4 plus 4 equal to 0, and a 0 on the denominator of a quantity does not give you any meaningful output. You see, x divided by 0, we don't know what it is. Now, why? Now, think about like this. What is 2 divided by 0.1? Now, think in your mind. 2 divided by 0.1 is 20. 2 divided by 0.01 is 200. 2 divided by 0.001 is 2000. That means as this denominator gets very close to 0, 0.000000001, the value of that quantity will be very large, 200 million. And when x is very, 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 very close to 0, the function value will be very, very, very large. And when x is equal to 0, we don't know what it will be. And that's the reason why we say a quantity, a number cannot be divided by 0. It doesn't give you any meaningful, understandable output. And therefore, you cannot use an input which does not give you a meaningful output. X equal to -4 is not in the domain of this function. Why is it not in the domain of the function? Because it does not give you a meaningful output. Now therefore, we say x equal to -4 is not in the domain, or look at the way the domain is written. -∞ to -4, union -4 to infinity, and this parenthesis signifies that -4 is not included. All reals are possible input here except -4. -4 is not in the domain of this function. Alright, look at the graph of this function. I want you to look at it for a while. This is x equal to -4. You can see the function graph has a break there. And watch what happens if x equal to -4.1 here. That is the output. X equal to -4.01. We are getting very close to -4. The output is very large. And as x gets closer and closer to -4, look at the language I'm going to use. X is approaching -4 from the left. Can you see that? X is approaching from -4.5, -4.4, -4.3, -4.2, -4.1. As x gets closer and closer to -4 from the left, where is the function output going? It's going towards positive infinity. In the same way, as x gets closer and closer to -4 from the right, -3.5, -3.6, -3.7, -3.8, -3.9, and it gets closer to -4, the output goes to -infinity. You see, there is a break in the function graph at x equal to -4. That means x equal to -4 does not give you a meaningful output. X equal to -4 is not in the domain. Now, how about the output of this function? How about the range? What is the meaning of range? Range is the set of all possible outputs. What is the range of this function? If you inspect this graph carefully, draw this graph in your calculator and say take a range of -1 to +2, you can see the function graph, the output can never be equal to 1. You will never get an output y equal to 1. That's right. Y equal to 1 is an impossible output for this function. The set of all possible outputs of a function is called the range of the function. Since in this case, y equal to 1 is not a possible output, we will write the range as -infinity to 1, union 1 to infinity. Again, look at the use of parentheses. It means the domain does not contain 1. I'm sorry, not the domain. The range does not contain 1. It contains all real numbers except 1. So, the domain is the set of all real numbers except x equal to -4. And the range is all real numbers except y equal to 1. Okay, let's look at another function. F of t equal to square root of t squared plus 3t minus 10. How do you find the domain and range of such a function? Well, first of all, you know that a quantity inside the square root sign cannot be less than 0. It cannot be negative. So to find the domain of this function, we would take the quantity inside the square root and set it greater than or equal to 0. T squared plus 3t minus 10 must be greater than or equal to 0. If this quantity is less than 0, then square root of that quantity will not be meaningful. There will be no output. So the values of t that makes this quantity greater than or equal to 0 are only the domains of this function. Now that's an easy way to find out what are the values of t that will make this quantity a positive quantity. Well, can you draw the graph of this on your calculator? Well, the graph will look like this. And look at the graph. You know that when a part of the graph is below the x-axis, it represents negative output. And the part of the graph above the x-axis represents positive output. Now, we cannot have values of t that will make this quantity negative. That means for all values of t that makes the graph below the x-axis cannot be used in the domain of this function. Do you understand that? You see, for all values of t from this 1, 2, 3, 4, yes, from -5 to 2. This is -5. If you watch here, -1 or -2, -4, -6. But this is -5. If you use any number greater than -5 or less than 2, it will give an output negative. The graph of that is negative. That means for any value of t greater than -5 and less than 2, this quantity will be negative, and the square root of a negative quantity will be undefined. Therefore, these values cannot be in the domain of this function. So an inspection of the graph of t squared plus 3t minus 10 shows that this quantity is negative in this interval, -5, less than t, less than 2. Between -5 and +2, this quantity is negative, and therefore these t values are not in the domain of this function. So the domain does not contain values from -5 to 2, and look at the way we write it. The domain is -5, -infinity to -5, union, 2 to infinity, and look at the brackets we have used here. What does that signify? It means -5 and +2 are included in the domain. You have domain values all the way from -infinity to -5 included are in the domain. And 2 to infinity, 2 included, are in the domain. But greater than -5 and less than 2 are not in the domain. That is what this means. And look at the graph of the function itself. This is the graph of the function. Don't confuse. This is the graph of the quantity inside the square root. And we did that to find out the values of t that will make this quantity negative. And this is the graph of the function square root t squared plus 3t minus 10. If you notice, there are no outputs for t between -5 and +2. Output exists only for inputs less than -5 and inputs greater than 2. That's right. Okay, look at the graph and tell me what is the range of this function. Well, the range are all possible outputs. There is no negative output. The minimum output is 0, and you can get any output greater than 0. Therefore, the range will be 0 to infinity, 0 included. So once again, the domain is negative infinity to negative 5, union 2 to infinity. No numbers between negative 5 and 2 are in the domain. And the range can be 0 and anything greater than 0. That is the range of the function. That means looking at the graph of a function, we can determine the domain and range of a function. That's a neat way to determine the domain and range of functions. Alright, what is the domain and range of f of x equal to ln x? Well, you're familiar with the logarithmic function, aren't you? Alright, what is ln of 1? Logarithm of 1 is 0. What is ln of 0.5? If you put in a calculator, you'll see ln of 0.5 is a negative quantity. ln of 0.1 will be a negative quantity. Now, how about ln of 0? ln of 0 is undefined. If you go back and look at how logarithmic functions are defined, you will understand why ln of 0 is undefined. Now look at the graph of f of x equal to ln x. And if you notice, ln of 1 is 0. And as x gets closer and closer to 0 from the left, is that right? This is x equal to 1. As x gets closer and closer to 0 here from the left, the output goes to negative infinity. That's right. That means the domain is only numbers from 0 to infinity, 0 not included, because ln of 0 is undefined. Look at the parenthesis there. And how about the range of this function? You can see the output can be any number from negative infinity to positive infinity. You get all outputs in here. Although inputs are only greater than 0, outputs can be any number. For numbers that are very, very small, close to 0, the output goes to negative infinity. So the range of this function is negative infinity to positive infinity. Let's now look at a similar function, g of x equal to e to the power of x. How does the graph of that look? G of x equal to e to the power of x. Well, that is the graph of e to the power of x. E to the power of 0, when the input is 0, the output is 1. And as the input is less than 0, the output approaches y equal to 0, but you can never get an output of 0 for this function. So the input can be any number from negative infinity to positive infinity. So the domain consists of all real numbers. So we write the domain is negative infinity to positive infinity. Any input can be used in here. E to the power of negative 10 is 1 over e to the power of 10. It's a very small number, close to 0, but not equal to 0. E to the power of negative 1000 is very, very, very close to 0, but not equal to 0. So the domain is negative infinity to positive infinity. The range only contains numbers that are greater than 0. So we will write the range is 0 to infinity, 0 not included. Now if you look at these two functions, you will see something strange or something, well, very interesting. What is that? The domain of the logarithmic function ln x is 0 to infinity. Its range is negative infinity to positive infinity. The domain of the exponential function is negative infinity to positive infinity. Its range is 0 to infinity. You see that? The range of the exponential function is the same as the domain of the logarithmic function. the domain of the exponential function is the same as the range of the logarithmic function. What do you call such two functions? Well, you have done that in pre-calculus, I'm sure. They are inverse of each other. So f of x equal to ln x and g of x equal to e to the power of x are inverse of each other. The domain of one function is the range of the other, and the range of one is the domain of the other. And also, if you now take this graph and keep it in here, you will see the graph of one is the reflection of the graph of the other along the line y equal to x. All these things discussed in your college algebra and pre-calculus class. We will now look at the meaning of continuity of a function. Now, having discussed the concept of domain, you must now know there are certain functions where some inputs will not give rise to any output. That means when there are no outputs, the function cannot be continuous there. You see, if the domain is negative infinity to positive infinity, and the range also is from negative infinity to positive infinity, the graph of the function will be continuous. There will be no break anywhere. For example, the graph of x of t equal to 2t. You can use any input, you will get an output. That means the function will be continuous, the graph will not have a break. If there is no break in the domain of a function, it is said to be continuous in its domain. That means a graph of a continuous function has no break in it. Look at the graph of, we looked at the graph of this, f of x equal to x over x plus 4. Do you remember that graph? I just showed it to you. It has a break at x equal to negative 4. That's right. In other words, we saw that as x gets closer and closer to negative 4 from the left, the output value, the function value goes to positive infinity. As x gets closer and closer to negative 4 from the right, the output of the function goes to negative infinity. There is, we say, a break at x equal to negative 4. The function is not continuous at x equal to negative 4. Now there's a break at x equal to negative 4. How about this function? Where does it have the break? X squared over 4 over x minus 2. Is it continuous all over or on the entire number line? Well, if you notice, the denominator contains x minus 2. That means when x minus 2 equal to 0, the function has a discontinuity. It doesn't give you a meaningful output. That's right. The graph of this function is here. Now look at the graph of the function. Can you look at this and tell me if you notice something? As x gets closer and closer to 2, you can see the function comes all the way here. This is very close to 4. Now, there is a hole here, which shows that at x equal to 2, you have no output. But anything greater than 2, yes, there is output. So, there is a break in the graph at x equal to 2. That means the function is continuous everywhere except at x equal to 2. At x equal to 2, there's a break, which means x equal to 2 is not in the domain of this function. All right. Discuss the continuity of the function x minus 1 over x plus 5 times x minus 2. What can you say about the continuity of this function? Well, in order to discuss the continuity of a function, you need to find the domain. Are there any values of x that is not in the domain? Well, if you notice, when x plus 5 equal to 0, the denominator will be 0, and that cannot be allowed. That means x equal to -5 is not in the domain of the function. Similarly, when x minus 2 equal to 0, the denominator will be 0 and there will be no meaningful output. Or x equal to 2 is not in the domain of the function. So the domain of the function does not contain x equal to -5 and x equal to 2. That means the function is not continuous at these two values of x. Look at the graph of that. As the input x get closer and closer to -5 from the left, I want you to pay attention to the left and right I'm using. As x get closer and closer to -5 from the left, the output goes to -infinity. As x get closer and closer to -5 from the right, the function output goes to +infinity. There's a break in the graph at x equal to -5. Similarly, as x get closer and closer to 2 from the left, the function value goes to -infinity. As x get closer and closer to +2 from the right, the output value goes to +infinity. There is a break in the function value at x equal to 2. That means the function is not continuous at x equal to -5 and x equal to -2. There are breaks in the function at these two values. All right. We will now look at the meaning of limit of a function. What is the meaning of limit of a function? Now, I was actually telling you when the input approaches a certain output from the left and from the right, the function value actually approaches certain value. Is that right? In the case of the first, when you have the denominator x plus 4, we notice that as x approached -4 from the left, what happened to the function value? Well, the function value either went to +infinity or -infinity. Is that right? Now we will use that concept to discuss what is called the limit of a function. Now let's take the case of the first function we talked about, a of t equal to 7.5t. Now, as time gets closer and closer to 1 hour, the amount A will get closer and closer to 750. Is that right? The student can say, oh, I have finished working half an hour. That means I can now take home $3.75. Is that right? Now, as the time gets closer and closer to 1 hour, you can say the output gets closer and closer to 750. And when x equal to 1, the output will be 7.5 because at t equal to 1, the function is continuous and we exactly know at t equal to 1, the value of the output is 7.5. Similarly, as x gets closer and closer to 5 hours, the output A will get closer and closer to $37.5. Now, we are now going to express these statements mathematically. We say, in the limit when t approaches 5, the amount A will approach 37.5. As t gets closer and closer to 5 hours, the amount of dollars get closer and closer to 37.5. Now here, t can approach 5 either from the left or from the right. Well, I know approaching t from the right has no physical meaning in here. It may be difficult for you to think about it, but t approaching 5 from the left has a meaning. Is that right? 4.5 hour, 4.6 hour, 4.7 hour, 4.8, 4.9, 4.99. Yes, I'm approaching 5 and my output is approaching 3750. Well, you can also think hypothetically as t approaches 5 from the right. 5.1, 5.01, 5.001, and finally t equal 5, it will give you the output 3750. And we write it like this: limit t approaches 5, 7.5t is 7.5 times 5, which is 37.5. So what did we do to find the limiting value of this function? Well, all we did is replaced t with that limiting value. We wanted to find the output of the function in the limit when t approaches 5, as t gets closer and closer to 5. What all we need to do is replace t in the function by that value. Now, that this is possible only if the function is continuous, keep in mind. Similarly, what is limit x approaches negative 2 of the value of 5x minus 2? Well, what all we need to do is replace that x by negative 2. So the limiting value of 5x plus 2. Now look at the way I'm reading this. The limiting value of 5x minus 2 when x approaches negative 2 can be obtained by simply replacing x by that negative 2. That would be 5 times negative 2 minus 2 equal to negative 12. One more time. Limit t approaches 5, the limiting value of 7.5t when t approaches 5 can be found by replacing this t by 5. Limit x approaches negative 2 of this quantity can be found by replacing x by negative 2. That's right. Now here, this tells you as x get closer and closer to negative 2, y get closer and closer to negative 12, and finally when x equal to negative 2, the function output is negative 12. Now, watch this. I'm putting down this as a definition. If a function is continuous at x equal to c, you can see in both these cases, the function is continuous at t equal to 5. The function is continuous at x equal to negative 2. So what we did here is valid only if the function is continuous in that particular limiting case. Now we're going to use x equal to c. In this case, c is negative 2, and in this case, t equal to 5. So if the function is continuous at x equal to c, then to find the limit as x approaches c, we simply replace the x value by the c value. This is the c value here. This is the c value there. So if the function is continuous at x equal to c, then to find the limiting value of the function as x approaches c, we replace x by c in the function and find its value. That is the method of evaluating a limit when the function is continuous at the point where we find the limit. Okay. How about this? Limit x approaches pi by 2 of sine x over x. Now, is this function continuous at x equal to pi by 2? Well, how do you know? Well, if you put x equal to pi by 2, what does it give you? Sine of pi by 2 is 1. So it will be 1 over pi by 2. Yes, it is continuous. In other words, an input of x equal to pi by 2 will give you a meaningful output. So what we are doing is to find the limiting value of this function when x approaches this c. This is our c. We replace x by this c value. That will be sine of pi by 2 divided by pi by 2. And you should know that sine of pi by 2 is 1. So that will be 1 over pi by 2. That is 2 by pi. Now, this is x equal to pi by 2. as x gets closer and closer to pi by 2, the function value is 2 over pi. Now once again, I want to emphasize here, x can approach pi by 2 from the left and also from the right, and in both these cases the output is the same. Alright? Okay. That is the point pi by 2, 2 over pi. That is, as x gets closer and closer to pi by 2, the function value gets closer and closer to 2 over pi, and ultimately when x equal to pi by 2, the output is 2 over pi. What happens if the function is not continuous at x equal to c? If the function is not continuous at x equal to c, replacing x by c will not give you any meaningful output, will it? No, it will not. For example, in this function, f of x equal to x over x plus 4, you know that from our discussion earlier, this function is not continuous at x equal to negative 4. So, if you want to find the limit when x approaches negative 4, can you find it by replacing x by negative 4? No, we cannot, because at that input there will be no meaningful output. So, once again, this is a beautiful graph. I hope you can see these numbers. The output I have used 300, negative 300, negative 200, negative 100, 0, 100, 200, 300, and so on. So you can see here, this is x equal to negative 4, and this is x equal to negative 5. So negative 4.5, negative 4.4, negative 4.3, negative 4.2, negative 4.1, negative 4, negative 4. Negative 3.9, negative 3.8, and so on. Now, what happens to f of x as x gets closer and closer to negative 4? Now, x can get closer to negative 4 either this way or this way. This way we call it from the left, and this one we call it from the right. Now, x can get closer to negative 4 either from the left or from the right. I hope you understand that. X can get closer to negative 4 as negative 4.5, negative 4.4, negative 4.3, negative 4.2, negative 4.1, negative 4.01, negative 4.001 is getting very close to negative 4 from the left. Similarly from the right, negative 3.9, negative 3.99, negative 3.999 is getting closer and closer to negative 4 from the right. Let's find the output values as x gets closer and closer to negative 4 from the left and from the right. Okay, let's start with x equal to negative 4.1, that is here. X equal to negative 4.1, use a calculator. X equal to negative 4.1, give me the value of the output. Do it on your calculator. It'll give you 41. So x equal to negative 4.1, the output is 41. What happens when x equal to negative 4.01? You can see now we are going closer to negative 4. When input is negative 4.01, the output is 401. So the input is somewhere here, the output is 401. And if the input is negative 4.001, we have actually gone very close to negative 4 from the left. The output is 4001. If the input is negative 4.0001, the output is 40,001. That means as x gets closer and closer to negative 4 from the left, the function output goes to positive infinity. The output increases without bounds. Alright. That means as x changes from negative 4.1 to negative 4.1 to negative 4.001, f of x changes from 41 to 401 to 4001, is going higher and higher and higher. So we can say as x approaches negative 4 from the left, the output approaches what? The output goes to positive infinity. That's right. Now, finally, when x is very close to negative 4, the function goes to positive infinity. And this is the way we write it. I want you to take note of this. We write it like this. The limiting value of the quantity x over x plus 4 when x approaches negative 4 from the left. Now look at the symbol we use for that. This negative power. It is really not a power. This negative sign here on the top right corner of the 4 tells you to read like this. X approaches negative 4 from the right. Oh, sorry. Negative means from the left. So limit x approaches negative 4 from the left. The value of x over x plus 4 is positive infinity. As x approaches negative 4 from the left, the output goes to positive infinity. And I want you to make sure you understand it. Alright. Now let's go to the other side. What happens when x gets closer and closer to negative 4 from the right? Let's start with negative 3.9 here. When x equal to negative 3.9, the output is negative 39. Here, that's negative 39. When x equal to negative 3.99, that is very close here. The output is negative 399. When the input is negative 3.999, very close to negative 4, the output is negative 3,999. That means as x gets closer and closer to negative 4 from the left, x gets closer to negative 4 from the left, the function output goes to where? Negative 3,909, negative 39,000, negative 390,000. It will go to negative infinity. That's right. So finally, when x is very close to negative 4, f of x approaches negative infinity. And how do we write it in a form like this? Alright, look at this. Limit x approaches negative 4 from the right. I want you to distinguish these two. That negative sign indicates from the left, the positive sign from the right. Limit x approaches negative 4 from the right, x over x plus 4 is negative infinity. So one more time. The limiting value of x over x plus 4 as x approaches negative 4 from the left is positive infinity. The limiting value of x over x plus 4 as x approaches negative 4 from the right is negative infinity. So the limit from the left is not the same as the limit from the right. Very important to know that. Okay. So the limit of this function as x approaches negative 4 from the left is not the same as the limit of this function when x approaches negative 4 from the right. Now therefore, tell me, what is the value of, if somebody asks you this question, what is the value of limit x approaches negative 4 of x over x plus 4? You see, to answer this question, you need to break it down into two pieces like we had, because the limit of this function when x approaches negative 4 from the left is not the same as the limiting value of this function when x approaches negative 4 from the right. And therefore, if somebody asks you this, the only thing you can say is that, I don't know. I don't know, because it's not clear. So we have no answer to this, because the limit from the left is not the same as the limit from the right. And we say in such a case, we can say that the limit does not exist. Such a limit does not exist. Why doesn't it exist? Because the limit from the left is not the same as the limit from the right. As x gets closer and closer to the c value from the left, the function goes to positive infinity. And as it gets closer and closer to the c value from the right, it goes to negative infinity. That means at that c value, the limiting value does not exist. If the limit when x approaches c from the left is not the same as the limit when x approaches c from the right, then the limit x approaches c, f of x does not exist. In order that limit x approaches c, f of x has to exist, the limit from the left has to be equal to the limit from the right. Okay. Let's now take the case of function f of x equal to x squared minus 4 over x minus 2. Now, what is the limit of this function as x approaches 2? Let's make a table again. Now, you can see x is approaching 2 from the left. That is, we are coming from 1.9, 1.99, 1.999, coming towards 2 from the left. The output increases from 3.9 to 3.99 to 3.999. What do you think is the ultimate goal? You see, if the input is now 1.9999, the output will be 3.9999. That means as x gets closer and closer to 2 from the left, the output is getting closer and closer to 4, isn't it? Yes. Similarly, let's come from the right. You are coming towards 2, say 2.1. When the input is 2.1, now use your calculator. Put x equal to 2.1 and find the value of this. It will be 4.1. X equal to 2.01. The output will be 4.01. When the input is 2.001, the output will be 4.001. You can see as x gets closer and closer to 2 from the right, the output is trying to get closer and closer to 4. Yes. So, in this case, as x gets closer and closer to 2 from the left, also closer and closer to 2 from the right, the output are both coming closer and closer to 4. What does that mean? Well, there you are. Well, what that means is the limit of f of x as x approaches 2 from the left is 4. As x approaches 2 from the left, the function value approaches 2. Now, this is the graphical representation. I have actually shown you this graph before. As x gets closer and closer to 2, the output is closer and closer to 4. Now, what is that point shown there? The input is 1.997 and so on. The output is 3.997 and so on. So, as x gets closer to 2, the output gets closer to 4. How about when x comes from the right side? We say the limit of f of x as x gets closer to 2 from the right is also 4. There is the next diagram. As x is getting closer to 4 from the, closer to 2 from the right. This is 2.0021. This is a value to the right of 2. And the output is 4.002 and so on. Now, what does that mean? It means that the limiting value of this function as x gets closer and closer to 2 from the left and as x get closer and closer to 2 from the right are both equal to 4. That means the output is the same as x approaches 2 from the left or from the right. And therefore, we can say limit x approaches 2 from the left, x squared minus 4 over x minus 2 is 4. Limit x approaches 2 from the right, x squared minus 4 over x minus 2 is also 4. And that means the limit from the left equal to the limit from the right. Therefore, we can confidently answer this question: what is limit x approaches 2 of this quantity? This time, we are not using left or right, because we now know the limit from the left equal to the limit from the right. Therefore, limit x approaches 2 of this function is 4. That means, in order that a limit may exist at x equal to c, the limit from the left and the limit from the right must be equal. If they are not equal, the limit does not exist. Alright, we have seen all this. Let's use that to make our general statement. Now, although the limit at x equal to 2 exists, the limit as x get closer and closer to 2 from the left and the right are both the same. Therefore, we say the limit exists. Well, but what is the value of f of 2? If you now put x equal to 2, you can see nothing comes out. That means f of 2 does not exist. You can see there's a hole there. And if you go to a calculator and do a calculation of the function at x equal to 2, the calculator will tell you y equal to, I don't know. There is no output. F of 2 does not exist. You see, the limit from the left exists, the limit from the right exists. Both limits come closer and closer to 4. So limit from the left equal to limit from the right. But the function value at x equal to 2 does not exist. That means the function is not continuous at that x value. There you are. You can see that hole right there. So therefore, we say the function is not continuous at x equal to 2. Now, look at the function f of x equal to x plus 2. Now, what is the limit, the limiting value of x plus 2 as x get closer and closer to 2 from the left? You can see x plus 2 is a continuous function. So it doesn't matter whether x is approaching from the left or approaching from the right. Its value will be 4, because what all we need to do in a continuous function is to replace x by the value of c. So that limit will be 2 plus 2, that is 4. How about limit x approaches 2 from the right of x plus 2? Again, this is a continuous function. Replace x by your c, and you get 4. And also, f of 2 equal to 4. Now, isn't this beautiful? The limiting value of this function at some c value. This is a c value we have. C is 2. You can see here, I have used 2 here, 2 here, and 2 here. That is our c value. As x get closer to some value c, if the limit from the left equal to 4, the limit from the right equal to 4, and the value of the function at that c value also equal to 4. Well, that means the function is continuous. The limit from the left equal to limit from the right equal to the function value, and that means the function is continuous at x equal to 2. So if I ask you, what is the condition for a function to be continuous at x equal to c, what will you tell me? In order that a function may be continuous at x equal to c, the limit x approaches c from the left must be equal to the limit x approaches c from the right, must be equal to the function value at x equal to c. Then we can say the function is continuous. There you have the graph of f of x equal to x plus 2, and it is continuous all along. There is no hole anywhere. A function f of x is continuous at x equal to c if, can you complete that for me? What are the conditions necessary for a function f of x to be continuous at x equal to c? Well, the limit x approaches c from the left of the function must be equal to the limit x approaches c from the right of the function, must be equal to the value of the function at c, f of c. Now, this is the necessary condition for the function to be continuous at x equal to c. It is not enough that the left limit equal to the right limit. We had it in an earlier case. But also the function value must be equal to that limit for the function to be continuous. Now we found that there are certain discontinuities in certain functions where the domain, depending on the domain values, if there are some domain values that are not allowed. In some cases, the discontinuities can be removed. Now, for example, this we saw, f of x equal to x squared minus 4 over x minus 2 is not continuous at x equal to 2. But you know, we talked about that. But we can simplify this. What is x squared minus 4? X squared minus 4 can be factored as x minus 2 times x plus 2. And divided by x minus 2, you notice that x minus 2 and x minus 2 will cancel. Actually, this rational function is the same as x plus 2. And you know, x plus 2 is continuous everywhere. Whereas x squared minus 4 divided by x minus 2 is not continuous at x equal to 2. Why? They are both the same. But when you have it in this form, there is no output for x equal to 2. That means this discontinuity can be removed by this algebraic process. What we have done is, we have removed the discontinuity by factoring and cancelling the common factors. So f of x equal to x plus 2 is continuous as x plus 2. That means we have removed the discontinuity there. Alright, try this. Remove the discontinuity and find or evaluate limit x approaches 1 of x squared plus x minus 2 over x squared minus 1. You see, if you now replace x equal to 1, what will you get? 1 squared plus 1 minus 2, that will be 0. And 1 squared minus 1 is 0. It will be 0 divided by 0. What is 0 divided by 0? Has no meaning. So, this has a discontinuity. At what point? At x equal to 1. Because at x equal to 1, the denominator becomes 0. But we can actually remove that discontinuity by algebraic process. What is that algebraic process? We can factor the numerator, factor the denominator. Alright, can you do that in your mind? How do you factor this? If you remember the method I had given you earlier, factor x squared and write it there x and x. Negative 2 can be factored either negative 2 times positive 1 or positive 2 times negative 1, which is the one that we need here. Because the middle term is positive, the bigger number must be positive. So, we're going to factor x squared plus x minus 2 is x plus 2 times x minus 1. X squared minus 1 is x plus 1 times x minus 1. And you notice the x minus 1 will cancel, leaving us x plus 2 over x plus 1. And now this is actually continuous at x equal to 1. Our c value is 1. Although this is not continuous at x equal to negative 1, we are not looking for the limit at x equal to negative 1. We are looking for the limit at x approaches 1. So since it is continuous at x equal to 1, we can replace our x by 1 now and find that limit. That will be 1 plus 2 over 1 plus 1. That is 3 over 2. The limiting value of this function when x approaches 1 is 3 over 2. And we did that by removing the discontinuity. I want you to practice this. Another one. Remove the discontinuity and evaluate the limit. Limit x approaches 3 of square root x plus 1 minus 2 over x minus 3. Well, this is a unique example. And the only way to simplify this is the understanding that the numerator square root x plus 1 minus 2 can be simplified if you multiply it by its, well, sort of like the conjugate. Now remember, a minus b times a plus b is a squared minus b squared. Now if you have some situation like that, we can remove the square root sign by doing that. So what we will be doing is, in this case, we have a discontinuity at x equal to 3, and therefore replacing by x equal to 3 is meaningless, because we want to find the limit when x approaches 3. And you know that at x equal to 3 we have a discontinuity. Therefore you cannot replace x in here by 3. And that means we should try and remove that discontinuity. Alright. What we're going to do is, we multiply the numerator and denominator by square root x plus 1 plus 2. Look at that, that quantity. And I want you to understand it like this. If this is a and this is b, this is a minus b, then this will be a plus b. What is a minus b times a plus b? It's a squared minus b squared. And that's why we are doing this. So we multiply the numerator by this quantity and also the denominator by the same quantity. Now look what we have done. Multiply the numerator by square root x plus 1 plus 2, and multiply the same at the denominator. And now, what is the numerator now? Can you tell me? This is a minus b times a plus b, and it will be a squared minus b squared. The square of this minus the square of this. What is the square of square root x plus 1? It is x plus 1. That's right. So it will be x plus 1 minus the square of 2 is 4. I hope you understood that. This will be a minus b times a plus b. It will be a squared, square root x plus 1 squared is x plus 1, minus b squared. And the denominator, we didn't do anything there. We will leave it at that. Now, what will we do? And that will be, if you simplify this, the numerator now is x plus 1 minus 4 is x minus 3. And look at that. That x minus 3 and that x minus 3 goes. By removing that x minus 3 from the denominator, we are removing the discontinuity. That's right. So that becomes limit x approaches 3, 1 over square root x plus 1 plus 2, because these have cancelled. And now, if you look, there is no discontinuity at x equal to 3 for this quantity. Therefore, we can find the limit by replacing x by 3. That will be 1 over square root 3 plus 1 plus 2. And that will be square root 4, which is 2. 2 plus 2, that will be 1/4. So the limiting value of this when x approaches 3 is 1/4. That's a beautiful problem. Try and practice that a couple of times on your own. Now, we have practiced evaluating limits. In many cases, drawing a graph will be useful to find the limit, although at one look it might appear that the limit does not exist. In many cases, where it appears that the limit may not exist, if you draw a graph, you can figure out the limit very well. For example, limit x approaches 0 sine x over x. Now, if you replace x by 0 here, will you get a meaningful output? No. So it looks like this limit does not exist. But let's draw the graph of this sine x over x. Put that in the calculator like this. y1 equal to sine x in parentheses divided by x. But make sure that your calculator is in radian mode. And this is the graph. The function output, the graph is from negative pi by 2 to pi by 2. So as x gets closer and closer to 0 from the left, what happened to the function? The function gets closer and closer to 1. As x gets closer and closer to 0 from the right, the function also is 1. That means what is the limiting value of sine x over x? The limiting value of sine x over x is actually, when x approaches 0, is 1. A little later on in calculus, I will give you a method of removing the discontinuity. Actually, you can remove the discontinuity in this case by a simple theorem that we will do later on. So the graph shows that as x approaches 0 from the left or approaches 0 from the right, the value of sine x over x approaches 1. So limit x approaches 0, sine x over x is actually 1. Now this can be expanded to limit x approaches 0, sine ax over ax equal to 1. The same process. So limit x approaches 0, sine of 5x over 5x will be 1. Limit x approaches 0, sine of 15x over 15x will be 1. Any of those forms will be therefore correct. Alright, evaluate graphically limit x approaches 0 of 1 minus cos x over x. Now here again, you notice that if you replace x by 0, you will not get a meaningful output. But we can actually remove the discontinuity, but at the moment you don't know how to do that. So we will draw a graph. Now look at the graph of 1 minus cos x over x. As x gets closer and closer to 0, the function is 0. You can see the function goes through the origin. So as x approaches 0 from the right, or from the left, or from the right, the function value is 0. So what's the value of that limit? Limit x approaches 0, 1 minus cos x over x equal to 0. That limiting value is 0. Okay. How about that? Find the value of limit x approaches 0 to sine 2x over 5x. Now remember, we just did a result. We said limit x approaches 0, sine of ax over ax equal to 1. Now can you use that over here? But the problem here is, this is sine 2x over 5x. Now, therefore, the task here is it possible for us to make the denominator a 2x instead of being a 5x? If we can have a 2x there, then limit x approaches 0, sine of 2x over 2x will be 1. You can actually do that with a simple process. So we are going to use this result. The result is limit x approaches 0, sine ax over ax equal to 1. Now look at what I have done. I multiplied the numerator by 2/5 and the denominator also by 2/5. Now, what did that do to the denominator? The denominator, you can see the 5 and 5 cancels. The denominator becomes 2x. That's what we want actually. And the numerator is 2 times 2, 4 over 5 is 4/5 sine 2x. And I can write it like this. That would be limit x approaches 0, 4/5 sine 2x over 2x. And this constant you can actually write outside the limit. So you can say that will be 4/5 times limit x approaches 0 sine 2x divided by 2x. And limit x approaches 0 sine 2x over 2x equal to 1. So what is the limiting value of that function? That will be 4/5. Alright, look at the graph of that. I drew the graph of this on the calculator. You can do that on your own. You can see as x gets closer and closer to 0, the value of the function approaches 4/5. That's 4/5, that's 1 there. So the limiting value is 4/5. Alright, let's do another one. Evaluate limit x approaches pi by 4 of tan x minus 1 over cos x minus sin x. Can you put in x equal to pi by 4 here? Try that. Tan pi by 4 is 1. So 1 minus 1 is 0. Cos pi by 4 is square root 2 over 2. Sin pi by 4 is square root 2 over 2. I'll give you 0 over 0. Well, we can actually remove this discontinuity by changing the tan to, look at this, tan x is written as sin x over cos x. And everything else remains the same. So tan x minus 1 is sin x over cos x minus 1. And in the next step, take the common denominator here and simplify. The common denominator is cos x. And if the common denominator is cos x, the numerator will be sin x minus cos x. So this is now sin x minus cos x over cos x divided by cos x minus sin x. And you can actually write it like this. This cos x actually belongs to the denominator. That will be negative cos x minus sin x. You see, sin x minus cos x is the same as negative of cos x minus sin x. Did you understand that? A minus B is negative of B minus A. That's what I have used there. Why did I do that? So that I can cancel these. So now, these two goes, you get limit x approaches pi by 4 of 1 over cos x. You can see that negative sign remains. And what is cos x? If you now replace your x by pi by 4, you can see this will become 1 over cos of pi by 4. So that's negative 1 over cos pi by 4. And that's equal to negative 1 over cos of pi by 4 is root 2 over 2. So that will be negative root 2 is that limit. I've actually done that limiting value for you. Here is pi by 2 negative root 2 as x approaches pi by 2 from the left, as x approaches pi by 2 from the right. The function value is negative root 2. Well, I want you to practice some of these skills on your own, and we are actually going to use these in developing the concept of calculus. All right?